Well, hey, you guys. Sorry for the low voice. I'm recording this kind of late at night, and I was thinking, man, my voice is a little scratchy, and everybody's in bed, and I have a chance to make this happen. So, thanks for stepping up if you're needed to help out today, because we're out running around checking out various kids' events, doctor appointments, and stuff like that. So, you guys can use Google Plus to send me messages. All this stuff I'm going to post on Google Plus too, so you can watch videos at home, get your homework, your sheets at home, and there's some keys for everything that you're doing today. So check in on those posts as well. All right, let's get started. We started talking about this yesterday anyhow. So take a look at this graph and make sure you kind of ponder it a little bit. You want to notice that the larger the base, those whole number bases, the faster the growth, that is, the steeper it gets. Don't forget you read left to right. And then for the smaller bases, the faster the decay. So that's a funny way to say that, but 1/10 is smaller than 1/2, and therefore it's decaying faster. So the larger the denominator of that fractional exponential curve, it's going to be a steeper descent, a quicker decay. So think of if I take 1/10 of something every time, I'm chopping it up into smaller and smaller pieces. A half of something doesn't chop it up quite as finely. Okay, so we got the growth side. If you point at it right there, and we got the decay side. Don't forget to read from left to right. Good sense of pattern if you're watching those graphs, and you'll be in a good place. Okay, so next piece. There's this example, the exponential function e to the x. We should revisit that, graph it for all its important parts. First off, we should note just the general shape of it. That part doesn't have to be that specific. But you do need to know that it goes through the point 0, 1. So we have that y-intercept 0, 1 is really important. And then from there, we can build all the other components, domain and range and x-intercepts, y-intercepts, and so on. So first off, let's talk a little bit about when it's decreasing. And let's just put it out there. It's not. If you read it from left to right, it's always increasing. Exponential curves are nice and consistent. When it's a growth function, it's always increasing. When it's a decay function, it's always decreasing. This one is a growth, so it's always increasing, never decreasing. So for increasing, you can write all reals or negative infinity to infinity. Either one is fine. I'm really liking this low voice thing. Then we should talk about end behavior, and that's when you should run x to infinity or negative infinity. Go to the extremes of x on the far right and extremes of x on the far left, and tell me what the function does. On the far right, as x goes to positive infinity, the function e to the x goes to infinity, and on the far left, if you go to negative infinity, the function goes to 0. There is that horizontal asymptote. So key features: y-intercept, horizontal asymptote at y equals 0. Let's get in domain and range just real quick. Domain is all reals, but the range is also from 0 to infinity. Be careful not to include 0, because it has an asymptote right there. All right, I'm going to move to the next page. If one of you is kind of keeping handy with the pause button, just request a pause. You're welcome to pause and rewind as necessary. I know I'm talking fast through this, but that's the beauty of the video format. Just pause and go back. There's no harm in doing that. But for the sake of those who want to go a little bit quicker and to keep the video from being crazy long, I'm just going to keep rolling. All right? Next piece, we got example 6. This is a transformation of that e to the x function. Now, we can actually do transformations in a variety of ways, but especially with exponential functions. But I'm going to keep it pretty straightforward for the first couple here. So let's talk about what this looks like. That 3 in front is up 3. It's not a stretch by 3. It's not some of the other things you might think it is. Maybe if you rewrote it and turned it around so that plus 3 is on the right-hand side, then you could see a little bit better. Kind of looks more like a plus 3 or an up 3. Okay, and then of course there's a -1 on the x. That's a right one. The negative in front of the e to the x is a vertical flip. That is over the x-axis. And all those things will make our e to the x function move around. So let's do them in order. You want to start with the horizontal transformation, right 1. So do that first. You do with that x stuff first, and specifically I want to start with left and right horizontal translations. Okay, and then we want to do that vertical flip. And I should probably whoa. My ninja writing got a little out of hand here. Hang on just a second. Let's slow this down a little bit. The vertical flip gets us to here. Let's just take this in pieces. All right, you see that upside down flip? Okay, over the x-axis, same thing mirrored over the x-axis. And then we're going to go up 4. So this whole upside down graph we have here is going up 4. But you know what else goes up 4? That horizontal asymptote. You want to move that as well. So make sure you get that up 4 as well. And now we can move not only that point that I have, the blue lines I indicated there, the vertical blue lines, are to show you going up 4. I'm moving that single point up 4, and I'm moving the horizontal asymptote up 4 to get this lovely graph. All right, this is a great place to pause, probably. The final graph there is highlighted in yellow, so you might want to take a peek at that and see what you can get out of it. But yeah, sorry, I ran into this one a little bit fast, and I didn't put enough pauses in my writing, so there you go. Take a look at that. That's got all the translations of that highlighted yellow graph is our final deal. Okay, I think I said up 4 a couple times too. It's up 3. All right, next we're going to go to that next example 7. Again, back up, pause as needed. All right, or send someone up there to the board to kind of clarify things a little bit if you need to. Okay, so the next one, I'm going to turn it around again. See that +4? I'm putting it on the right-hand side. I'm just going to identify all the transformations first. Okay, and there we got our vertical flip. We got a notice the horizontal flip. That's a tough one. That -x. We also have that +5 in with the 7 to the 5 minus x. That +5 in the exponent. That's a left 5. Horizontal flip because it's -x and a left 5. So take a peek at all those. Vertical stretch by 3, vertical flip, up 4, left 5, and horizontal flip. That's a lot of stuff. And of course order is going to make a difference here, so let's get a graph going. The first thing I'm going to do is I'm going to take, with an exponential curve, you can think of that 3 out in front as kind of your initial value. Can be your y-intercept is another way to think about it. It's where you start this curve out. And because it's vertically flipped and it's 3, I'm going to put a dot, kind of that y-intercept point at -3. That's where I'm starting this thing out. Okay, so I put a dot there at -3. Notice that. All right, and then I'm going to take this thing left 5. So the first things I usually do is that in an exponential is you want to get that y-intercept placed somehow if you can. And we did with that -3 kind of initial value. Then we went left 5. Now I'm going to apply the horizontal flip to the other side of the y-axis. I'm going to flip it over. Okay, so there's that horizontal flip. So we did left 5, horizontal flip. And notice that I'm just moving around that initial point, that y-intercept that goes with the curve. Okay. I'm going to start drawing in the graphs a little bit later. Then we're going to go up 4, and what that means is I'm going to move the horizontal asymptote up 4. Now, I'm also going to move that point up 4. So let's take this back just a quick step. I'm actually going to draw on the graph at each step. So I'm going to move the point. I went to -3. I started it at -3, the initial value of -3. Then I went left 5. Then I did a horizontal flip. Then I'm moving that point up 4 as well as the horizontal asymptote up 4. I'm going to go back to the beginning here. I'm going to put the graph in there for each of these steps. All right, so when we first put it at -3 and vertically flipped it, we have an upside down exponential curve going through -3. There's that first part. And then I went left 5. Then I flipped it over. Okay, and when I do that, it's turned around backwards. And then I moved it up 4. Done deal. Okay, that's the rest of it. And I highlighted there in blue. That's a tricky one, a lot of movement, but I just want to get back into the world of transformations and how they look and the process and the order that you take. Check in with who is ever available that might be able to back this up and explain that a little bit better. So tag somebody who knows pretty good at this stuff. Next one. Example 8. So let's talk about transformations on these basic functions. There are multiple ways we can talk about transformations, especially with exponentials. So I'm going to do 2 ways for each. Okay, so let's talk about the first one. All right. I think the easiest way to describe part A, or letter A, is it's 3 to the x shifted right 1. I don't think anybody's going to argue that. We can graph it pretty easily. However, what I want to talk about is I can actually rewrite 3 to the x minus 1 as 3 to the x over 1. I'm sorry, 3 to the x over 3 to the 1. Do you remember that rule that if you put the same bases over top of each other, that you subtract their exponents? Now think about that. 3 to the x over 3 to the 1 means it would be equal to 3 to the x minus 1, which is what I have. So the process of doing that, I'm able to rewrite this, so I'm just giving you one step at a time. 3 to the x minus 1 is equal to what you're seeing there on the right-hand side, 3 to the x over 3 to the 1. Back and forth, you can go between those two things. Now, I'm going to keep rolling. I'm going to redo this one more time. That 3 to the 1 on the bottom, I'm going to bring it out as a 1/3 out front. Still have times 3 to the x. Now this gives you a different look at the exponential. That 1/3 in front of 3 to the x is like our initial value. Remember, so with exponential functions, something you multiply by the base to the x. That's our a times b to the x, where a, our initial amount, is 1/3 times b, which is 3 to the x. Okay, it's a little bit different perspective. It means instead of a shifting to the right one, we're now looking at something that looks like a vertical shrink of 1/3 on the 3 to the x curve, and it is. You could look at this as a vertical shrink of 1/3. Okay, so let's look 3 to the x. Alright, if I shift it right 1, I'm going to go ahead and put a little line in there that makes this a little bit clearer. Okay, see if I can get this on here. Alright, color, hang with me. Yellow's too shallow. The color needs a little more pop. Let's throw that wacky purple in there. So, to the right 1 looks like that. Okay, I'm moving that graph to the right 1. Bingo. Okay, does that look good? Alright, oh, wait, I've got it in green already. Now, the other way to look at that is, what if I took the graph and just shrunk it by 1/3, brought everything down 1/3 of its original height? Now, if you're noticing, you get the same result. To move right 3 or shrink everything down 1/3 creates the exact same graph. So it actually describes it the same function. So knowing these rules of exponents and how they work allows you to rewrite them in a different form. So the one that we just highlighted there is that 3 to the x minus 1. When you subtract two exponents, remember that's when you have same base over same base, one on top and one on bottom. You can write that as the difference of those two. So you can write it as a single 3 to the x minus 1. Cool, that's a way to rewrite it. So we use exponent rules to write this in a different form. You get the same graphical result, just a different way to think about it. Okay, next one. Let's do this one in standard form. All right, 9. We're supposed to rewrite this 9 to the x plus 2 and how it's been transformed from 3 to the x. Well, we're looking at this as a left 2, usually. That'd be like our standard look at this. But the thing is it's how are we transforming it from 3 to the x? What that means is I need to change this function into a base 3 exponential. So here's how I'm going to do this. Instead of calling that 9, I'm going to call it 3 squared to the x plus 2. That changed the base into a base 3. Now, knowing my exponent rules, when you have a power of a power, you can distribute that. You can multiply them together. So power of a power, you multiply. So we're going to call that 2x plus 4. Okay, so 3 to the 2x plus 4. And having rewritten it that way, that can give us, that's the information we need for a transformation on 3 to the x. We can talk about this in detail. All right, we got a left 4, and we've got a horizontal shrink of a half. Okay, so let's see how that plays out. Here goes. If I graph this a little bit more, I'm going to graph it, here's 9 to the x. All right, hitting 9. I'm sorry, I wrote 9 to the x in there, but I think I meant to write 3 to the x. But, well, let's start with 9 to the x and see how that goes. Okay. All right, 9 to the x minus 2. If I just shift it left 2, there it is. All right, let's just go with this. This is what I wrote the first time through this. Okay, so there's 9 to the x minus 2. What do you think? Does that seem reasonable? You got the idea? I'm taking 9 to the x. If I shift it left 2, this is the graph that I get. No big deal. Okay, 9 to the x minus 2. Just trying to get the page in there. Now, let's take that. I'm going to do it a little bit differently. Let's use the next option that we have. That 9 to the x minus 2, got the graph, everything's groovy. Now what if I did the second transformation, and I highlight this in green, this one right here. If I take 3 to the x, and I go left 4 and I shrink it by a half, what's interesting about that is 9 to the x and 3 to the x have a similar type of behavior. They both go through the point 0, 1. Okay. And then, but one thing that's different about them, let's look at this a little bit differently. Oh, sorry about that. Put that back in place. If I keep going, if I shift this to the left 4, that original graph, and then I shrink it by a half, so I make it half as wide, can you see what happens in here? That left 4 point, if I horizontally shrink it by a half, instead of left 4, that'll be a left 2. That's not the end of the story. So there's that horizontal shrink, brings back to left 2. But it also takes the different shapes of those. 9 to the x is a very different, that's a very steep curve. Remember, 9 to the x is really steep? Well, that horizontal shrink, that process of doing that, transforms that particular aspect of it too. If I take a 3 to the x curve, which is less, and I meant to draw this in here earlier, and so I didn't do that. That's what's probably making this a mess. Here's 3 to the x, has the same 0, 1 intercept. But if I shift it left 4 and then horizontally shrink it by a half, what it does is it puts it through the same coordinate points, but it also brings it steeper, because when you shrink it horizontally, it takes that broad look of that 3 to the x curve and it makes it more steep. So it has the same effect when you're done. Now, the idea is not to try and graph these perfectly and see that they match up. What you're trying to do is get the idea that, in general, I understand that if I graph 9 to the x plus 2, can you see the idea that 3 to the 2x plus 4 by transformation gives you the same type of function? If you put them in decimals together side by side, they graph the exact same function. Okay, so we're just trying to make that connection that there's multiple ways to represent these, and it just depends on what's most useful for your situation. Okay, I'm going to go to the next idea, and this is a different direction to go. This is a quick transition. This is one of those places where if you want to pause and go back, you can. If not, just keep rolling with it. You guys are going to do a worksheet related to this, for which a key is posted. And so some of the things I'm explaining are so you can understand what's on that key and ask some really smart questions like you guys are apt to do. This video is up to 17 minutes. My goal is to try and get in before 25 minutes so that you can make this reasonable if you play it for yourself at home. Okay. What we're going to do is we're going to get a y equals a times b to the x function given the points that I have. 225. The other point is 1, 5. I marked it with a green dot there. So we're going to use a system of equations to make this happen. There's two different x's and y's that I can plug into my equation. So I put them both in here. Can you see the first and the second? I'm going to kind of highlight those. Here's my first, and then here is my second function, if I can get that to work. There we go. I don't know. Having some issues with my computer here. There we go. Seems like I can't get a color that I want for my highlighter. Oh, there we go. Much better. Purple. So there's one and there's another one. Okay. Let's work through the rest of it. I'm going to actually solve for a in that right-hand equation, and then sub that in for a in the left-hand equation. Okay? You see where that's getting placed? So what we're doing is we're putting in both x's and y's that we have. We have two, each into their own y equals a times b to the x function. We're going to solve for a variable in one equation and sub it into the other. It's classic substitution. So got myself a little place to substitute. I wrote it in there. It's really tiny. Hopefully you guys can see this. The other part is when I use this software, it's really tiny. Feel free to walk up and sit in front of the screen so you can see a little bit better. And there we are. So those cancel. The b's and the b squared cancels just to a b. So 25 equals 5b. Because the b squared and the b canceled with each other down to a b to the first. And if you divide both sides by 5, you get 5 equals b. That's part of it. We need an a still, but we do have that that b equals 5. Well, again, if b equals 5, then we can just do another substitution in that right-hand equation. I can put 5 in for the b on the right-hand side there. We got 5 over 5. We got a equals 1. Once you have a and b, you need to write a brand new equation, so you want to make sure you have it all. Y equals 1, my a, times b, which is 5 to the x. Y equals 1 times 5 to the x. We all know that we don't need the 1, so it's just y equals 5 to the x. And if you check it out, it makes sense. Given the values that we have, when you put in x equals 1, 5 to the first is 5, and when you put in x equals 2, you get out 25. Life is good. Second equation. All right, let's do the same thing. We have 2 points, 0, 1, and 3 and 1/8. Okay, so I already put it 0 and 1 for x and y. I'm going to do the same for, okay, and that's a quick solve. B to the 0 is 1. That means in that case a equals 1. See if you can wrap your head around that one. That's a pretty quick solve. And it goes through, has a y-intercept of 0, 1. That sets us off on a pretty nice pace. We can already decide that a equals 1. If you can remember, by the way, this value up front there, that really is, it's has many descriptors. We can call it the initial, it can be called just the y-intercept or the initial value. That's one way to describe it. These are all good things to say about it. That a value is the initial value. You can call it the y-intercept. There's a few other ways. Think of it as a vertical stretch. All those things are valid ways to think about what that a value stands for. Alright, so if I got a equals 1, now I can use that in another equation. Y equals 1 times b to the x. Let's use the other point, 1/8 and 3 for y and x. So 1/8 in for y, 3 goes in for x. Solving for b, if I want to get b by itself in this situation, you have to take the cube root of both sides or raise both sides to the 1/3. Same idea. Raise it to the 1/3 of cube root. So I'm going to do the cube root of both sides. The cube root of cube root of 1/8 is 1/2. 2 times 2 times 2 is 8. So we've got the nice solid 1/2 for b, and we got a great looking equation. So I got the a equals 1 and b equals 1/2. I'm going to write it up at the top here. Oh, got a little issue here. It's y equals 1/2 to the x. Sorry, I wrote over some stuff that I already had written in there. So y equals 1/2 to the x. Hope you can find it in there. That's kind of gross looking. There we go. Y equals 1/2 to the x. It's hidden in there. Rolling on. Okay. That initial value, just keep that in mind. The a is an initial value or a y-intercept. They're both reasonable ways to describe a. Let's keep on it going. I gotta get to my next slide. Go. Go, computer. Go. Go. Alright, I'll make it work enough. There we are. Down below. Example 10. Let's start with the first one. Something about that last problem. We learned that that initial value is also the y-intercept. Well, since in part A, 0, 4 is a y-intercept, that could be interpreted as my initial value. That's my a. So a is 4 in part A. Go to part B. That's a y-intercept, 0, 2. That's my initial value. That's my seed in this exponential growth. That is going to be my a value. Okay, 2 is going to be a in this problem without having to think too hard about it. So let's go ahead and start with that way. So in part A, 4 is my a times b to the x. I just use the other point, 522, for x and y. And then we just solve for b to get that piece of the equation. Now these are not clean. There's nothing about these that's going to look good to you, but it's about sticking to get your a, get your b, plug them into y equals a times b to the x regardless of what they look like. We'll simplify later. Okay, I'm going to divide both sides by 4 to get b to the 5th by itself. And I hope you're okay with it. I went ahead and simplified that to 11 halves. The only thing left to do is get b by itself is to take the 5th root of both sides to undo that b to the 5th. And so we'll raise each side to the 1/5, and there you have it. That's our equation. We have an a of 4 because it was our initial value. A y-intercept is an initial value. So if I look at this, that 0, 4 y-intercept is our initial value. It is our a. Okay, so if you happen to be handed a y-intercept, you're actually being handed an a value, the start of your exponential function. Okay, and when you plug this in, by the way, look out. Just use parentheses really carefully. You don't need to do any crazy simplification. 11 halves to the 1/5, as much as you may not like it looking like that, it's okay. Just make sure that goes in the place where b is located in that equation. Alright, let's do another one. Initial value of 2, so that's our a value. we are going to put in 3 and 1/2 for x and y respectively. Okay, so I did that substitution for you. We are going to solve for b by dividing both sides by 2. A half divided by 2 is 1/4. And then we're going to cube root both sides or raise it to the 1/3 power. Either one's fine. Now we can write it. We're good to go. We have an a of 2 and a b of 1/4 to the 1/3. And then all that 1/4, the b gets raised to the x, not the a. The b value is the only thing that gets raised to the x. That's why I put brackets around the 1/4 to the 1/3 bracket to the x power. Only b gets raised to the x power. A sits out front. Rolling on. We're getting to the end. I told you 25 minutes was my goal. Well, I'm not going to make it. So we're going to do a last 2, and this is probably going to push us to at least 30 minutes. Same thing we just got done doing, but the problems aren't as clean. So what's going to happen is we're going to do that substitution process again. So I'm going to use one of the points, 10, -2, to put in for x and y. For the other point, I'm going to use 1/3 and 2. We're going to solve for a in one of those equations. We're going to use the left-hand one. It seemed like the easier. Remember, b to the -2 is also, you can put it in the denominator as b squared on the left-hand side there. So I can multiply both sides by b squared, that denominator, and I've got a by itself. Now I can sub that into the right-hand equation, where a is located, that b squared, 10 times b to the second. So 1/3 equals 10 times b to the second. Goes in 4a. Okay. And then this is the crazy part. Now I'm going to back this up a little. Sorry, it went kind of crazy for a while there. I'm going to divide both sides by 10 after that substitution, and that makes 1/30th on the left. And if you notice that b squared times b squared is b to the 4th. Okay, so just a little bit further there. That's a good place to kind of pause and wait for a second. Okay. Now, once you've got that, we can take the 4th root of both sides and just get b. There's our b, 1/30th to the 1/4. A lot of fractional things going on here. And we can use that same b to find our a on the left-hand side, where we last left off. So we'll just put 1/30th to the 1/4 in for b, where b is being squared on the left side. We just substitute it directly in for b. Now we're squaring that crazy fraction. And we got our a. A is a mess. There's a lot of stuff going on in there. We're going to put it all together. The only thing I would suggest is there is this 1/4 to the 1/3. I'm going to get my highlighter going again. Let's see if I can make this happen. Here we go. A lot of stuff happening on this thing here. Can't get my highlights to work. There we go. That's what I wanted. Green. This 1/4 to the 1/3 that you see right there. Maybe I should highlight it. That, if you take a power of a power, you multiply, and 2 times 1/4 is just 1/2, and so that's what you see right there. Power of a power, I just multiplied 2 times 1/4. Okay. We got an a, we got a b. I'm just going to put them together as a single equation. Sorry, I got to get that past there. So another way to write a is, if you're going to take 10 times 1/30th to the 1/2, that could be 10 times the square, 1 to the 1/2 over 30 to the 1/2, and a 1/2 power is a radical. I just went ahead and simplified a little bit further. You could actually, from that place, just put a and b beside each other, making sure you only raise b to the x power. So if you want to simplify as I've done in this video, this particular video, that's great. I'm just using radicals as opposed to fractional exponent powers. You're welcome to keep the originals. How you write a and what you left off at, this a over here that I highlighted in blue right now, that's perfectly fine. This b that I'm circling right now is perfectly fine, as long as you only raise the b to the x power when you put it all together. Okay. Alright, let's keep on it going. We gotta get this video done. The last piece, one more of these crazy problems. These are tricky. Okay, we're gonna put x and y in to the equation, y equals a times b to the x. Solve for a in one of those. I think the left-hand side is a little easier. Now, this is a little trick that I did not illuminate very well, but I'm going to go ahead and do my best to try and show you. A times b to the -5th is the same as, ooh, brown color. There we go. is the same as a over b to the fifth. Okay, and if I multiply both sides by that b to the fifth, you get what you see right here on the left-hand side. So a times b to the negative fifth is the same as a over b to the fifth. And then if I multiply both sides by b to the fifth, we get 1/8 b to the fifth equals a. Rolling on. Okay, that's our a. We can use it anytime, anywhere. If I substitute that in, this 1/8 b to the fifth, over here on the right-hand side where a used to be, get a nice little substitution. I see b to the fifth times b to the fourth. In that case, when you're multiplying same bases, you add the exponents, so it's going to be b to the ninth. And the 1/8, if I multiply both sides by 8, the left and the right, to get rid of that 1/8, I get 64 on the left. So this is from times 8 times 8. On the right-hand side, you get 64 equals b to the ninth. And finally, to get rid of the ninth power, you take the ninth root. So if you have 64 equals b to the ninth, you do 64 to the 1/9, you have b. Alright, we got our a and our b. Now we need to use this brand new b and sub it in for b on the left-hand side. Okay, so we're going to put it back in there. And if we work this out, we're good to stop if you put in 64 to the 1/9 in for b and raise it all to the fifth. What we have is a power of a power. 1/9 to the fifth, that's 5/9 that you see down here. And there's our a. Okay, so we have a b right here. We got an a down here on the bottom. Together, we're just going to write y equals that crazy a times b. Oops, I highlighted the wrong b. Sorry about that. Let's back that up here. Here's our b. 64 to the 1/9. Sorry about that. And then I got our a, our crazy a down here. We'll put those together in a single equation, which you'll see up above. Whoopsie. Gotta back that up a little bit. If you see up top there, just take that a as it is, put it out front, and then you raise the b to the x power, and you're done. There's other things that we can do later, but for right now, that's the idea, is being able to isolate a and b, put it into an equation to finish things off. That is the story. We'll talk more about logistics when I get back. 30 minutes. Hope you guys made it okay. That's pretty extensive. And feel free to check this out again at home to kind of fill in the gaps. And I'll be back on Friday to help you kind of digest more of this. This will take a few days. There's a lot going on in here. Enjoy, and thanks for being awesome as you guys are.